Hello, welcome back. Today let us talk about the energy of elastic vibration in crystals. So the energy of elastic vibration is quantized and the quantum of the energy is called phonons. This is exactly like the case of electromagnetic radiation where the quantum of an electromagnetic radiation is called photons. Energy of an elastic mode of vibration of frequency omega is given by the E is equal to n plus half h cross omega, where n represents the nth excited state, to which the um, uh, the mode is excited, or the or we can say that the mode contains n photons. Mode is occupied by n phonons. So this is the energy of an elastic mode whose frequency is omega. So n plus half h. Here half h cross omega is called the 0 point energy, the lowest energy. So the energy of a vibration is equal to n plus half h cross omega. It is also analogous to the case of harmonic oscillator. So that means elastic vibration can be considered as the collection of harmonic oscillators. These phonons will interact with the particles like X-rays, that means photons, neutrons, electrons, and even with other phonons, as if they had a momentum h cross k. But these phonons will not possess physical momentum. That means phonon doesn't have a momentum. But if we see, for most practical purposes, the phonon behaves like it possesses a momentum which is equal to h cross k. H cross k. So this momentum may be termed as crystal momentum. Okay, so a phonon doesn't have actually physical momentum, but it behaves like it possesses a momentum of h cross k. Okay, we know that in crystals the elastic scattering of photons or the X-rays is governed by the selection rule of the wave vector given by k dash is equal to vector k plus g. Okay, so this is for elastic scattering of photons by crystals. Okay, here k is the incident wave vector and k dash is the scattered wave vector. Okay, for inelastic scattering, that means here the total energy is conserved. For inelastic scattering, what happens? This k dash plus some new phonon is produced. So k dash plus k is equal to small k plus g. In addition to the scattered photon, a phonon also produced in this process. So that's why this is called inelastic scattering. Inelastic here a phonon is created. Okay. In some cases, a phonon is absorbed. So the equation of motion or equation of the wave vector is given by k, small k. This is for the photon minus k, or we can write k dash is equal to small k plus a phonon absorbed plus g. Okay. So this is actually k dash minus k. A phonon is absorbed. So we can take this minus k to this side. So therefore k dash is equal to k plus capital K for phonon, and g is the reciprocal lattice vector in all these equations. Okay. So this is, in this case, phonon is absorbed. So anyway, this phonon behaves like it possesses an energy, sorry, a momentum h cross k. If we multiply h cross on either side of all these equations, we get the equation of law of conservation of momentum. So the momentum for the entire system is always conserved. This was the scattering of a photon by phonons. Now next we can see the scattering of a neutron beam by phonons. Using an experiment, it is possible to determine the relation between the omega and k of phonons or elastic vibrations. Okay. For that, let us consider the inelastic scattering of neutrons by phonons. So the scattering of neutron is from the actually the nuclei of the atoms. Okay. So the selection rule for the wave vector of neutron is given by k dash plus capital K plus or minus capital K is equal to k plus g. Here small k vector is the propagation vector of the incident neutron, and k dash is the scattered neutron beam wave vector. K is the wave vector of the phonon, and g is the reciprocal lattice vector. Here plus k refers to the created phonon, plus represents the phonon created, minus s means phonon absorbed. Phonon is absorbed in this process. Okay. So the general equation is k plus or minus capital K is equal to k plus g. Here g is selected in such a way that, so this is in the first Brillouin zone. Okay. So if it goes outside the first Brillouin zone, what happens? The addition of this g brings the wave vector into the first Brillouin zone. So this is also called the momentum conservation. If we multiply h cross in all these equations, we can write this in terms of the momentum. Okay. So this is the equation of momentum, or the law of conservation of moment. Now, law of conservation of energy. Law of conservation of energy is the energy of the incident neutron beam, that is incident neutron has energy is equal to p square by 2 mn, a single neutron. So p square by 2 mn, where mn is the mass of the neutron. And what is p? P is equal to h cross small k. So h cross square k square by 2 mn. So this is the incident energy of the neutron. Now the scattered neutron energy is given by p dash square. So that is h square k dash square by 2 mn. Okay. So therefore Here, since this is inelastic scattering, so the total energy of the phonon is not conserved. Sorry, total energy of the neutron is not conserved. Therefore, mm, we can write the total energy h cross k dash square divided by 2mn plus or minus energy of phonon h cross omega, which is equal to h cross square k square by 2 mn. Here the plus h cross omega is the energy of phonon created, and minus h cross omega corresponds to the energy of the phonon absorbed. So in a process, either of these two happens. Okay. So if we find out this value of energy loss or gain, we can find out the dispersion relation from this. Okay, using equation. This is equation 1 and equation 2. So using equation 1 and 2, we can find out the relationship between omega and k. So like this, we can experimentally determine the dispersion relation. That is the relation between omega and k of crystal vibration. Okay. So we can draw a graph. A graph is plotted in Kittel. You can see that. So here I'm drawing this graph here. This is Kmax and 0. And here angular frequency, actually frequency is given, nu is given. So it is plotted like this. Graph is plotted like this. So this is experimental curve. We know this is what? This is nothing but the acoustic mode of vibration. So today we have discussed quantization of energy of vibration. So energy of elastic mode is given by n plus half h cross omega. Then we have seen the momentum conservation laws, that is the equation of the wave vectors in the case of elastic scattering and inelastic scattering. Okay. In the case of inelastic scattering, a phonon is absorbed or released or created. Okay. So similarly, corresponding energy also will be lost in the form of phonon. Okay, that's all. Thank you.